So, you're in a differential equations class, right? And you learn all these cool tricks, but then you hit a problem you just can't solve with a neat formula. What do? Well, that's where Euler's method comes in. It's this awesome tool for approximating solutions when the exact answer is just impossible to find. So here's what we're going to do. We'll start with why we even need this thing. Then we'll get into the big idea behind it, walk through the actual recipe, and of course, try it out on a real problem. And stick around, because at the end, we're going to talk about its one big weakness, which is super important to know. All right, section 1. This is all about why our usual methods sometimes just fail. Okay, so you've spent all this time in calculus, right? You've mastered separation of variables, you know your integrating factors, and you feel pretty good. But then your professor throws an equation at you where nothing works. What are you supposed to do then? And here's the thing, that's actually the norm. Most of the differential equations that describe real-world stuff, like physics or economics, can't be solved with those neat little tricks. They're just too messy. And that's exactly why we need a totally different game plan. Okay, so if we can't find the perfect formula, what's plan B? Well, the idea is actually pretty brilliant. Instead of trying to find the entire solution all at once, we're just gonna build it, one little piece at a time. And that brings us to Euler's method. You've got to love the core idea here. It's super visual. Forget finding some complicated curvy function. Instead, we're going to cheat a little. We'll approximate the curve by stringing together a bunch of tiny straight tangent lines. It's like we're stitching together a solution. I love this quote. Think about it this way. You're standing on a hill, blindfolded. All you know is the slope of the ground right under your feet. So what do? You take one small step in the steepest downward direction. Then you stop. Feel the new slope, and take another small step. You're basically building a path down the hill, step by step. Okay, that's a cool idea, but how do we turn it into something we can actually use? You know, an actual algorithm? Let's check out the recipe. It's really just a simple loop. You start somewhere, you figure out which direction to go, that's your slope, you take a tiny step, and boom, you're at a new point. Then what? You just do it all over again, and again, and again. Now, the formula might look a little scary at first, but don't let it fool you. It's exactly what we just described. Your next position, y sub n plus 1, is just your current position, y sub n, plus a little push. And that push is just your step size, h, multiplied by your current slope. See? New value equals old value plus a small step in the right direction. That's it. Okay, theory is great, but let's get our hands dirty. It's time to actually run through a problem and see how this thing works. So here's our mission. The differential equation is y prime equals x plus y. That just tells us the slope at any point. We know we're starting at the point 0, 1, and we're going to take steps of size 0.1. The goal? Figure out the value of y when x gets to 0.2. All right, let's do the first step. We start at x equals 0, y equals 1. What's the slope there? Easy, it's x plus y, so 0 plus 1 is 1. Now we plug it into our recipe. The new y is the old y, which is 1, plus our step size, 0.1, times that slope of 1. Do the math, and we get 1.1. That's our very first approximation. And now we just repeat the process. Our new starting point is x equals 0.1 and y equals 1.1. So, what's the new slope? 0.1 plus 1.1 is 1.2. Back to the formula. Our next y is our current y, 1.1, plus the step size, 0.1, times our new slope, 1.2. A little multiplication and addition later, and we land on 1.22. And there we have it. After just 2 steps, we've arrived at x equals 0.2, and our estimate for y is 1.22. Pretty straightforward, right? But now for the million-dollar question. How good is that answer? Well, if you were to solve this one exactly, the real answer is about 1.2428. So our 1.22? Not bad. It's definitely in the ballpark. This proves the method actually gets us close. But it also proves it isn't perfect. And figuring out why it's off is a really, really important part of this whole thing. Which brings us to our final section, digging into that error. Where does it come from? And can we predict it? So here's the big question when you're doing any kind of approximation. It's not just that you're wrong, but how you're wrong. Did our method give us an answer that was too high or too low?
And the answer to that question comes from a concept you probably remember, concavity. To figure it out, we look at the second derivative. A positive second derivative means the curve is concave up. You know, like a cup. A negative one means it's concave down, like a frown. In our example, it turns out the second derivative is positive. so our true solution is always curving upwards.
Okay, now this is the whole key right here. Picture a curve that's concave up. It's always bending upwards. A tangent line touches it at one point and then shoots off straight. Because the real curve is bending away from that straight line, the curve itself will always be above its tangent lines. And since Euler's method is literally just following those tangent lines step by step, and those tangent lines are always underneath the real curve, our approximation is always going to be playing catch up. It's always going to underestimate the true value. And hey, that's exactly what happened in our example, right? 1.22 is less than 1.2428. So that leaves us with one last thing to think about. We know that to get a more accurate answer, we could just use a smaller step size, take more steps. But what's the catch? Well, every step is a calculation. So a smaller step size means more accuracy, but it also means way more work for your computer. And that trade-off, that constant battle between accuracy and efficiency, is really what the entire field of numerical methods is all about.